Okay, we started with the generalized finite element method. The first thing we did was to look at some definitions. So we defined what was the open cover, or the cloud or support, and you can think of the support or the cloud of a node as just basically the elements that are connected to the node, and or you can also think as the domain or the part of the domain where the shape function associated to that node is non-zero. That's basically what it is. We look at the idea or the what is a partition of unity, and it's just defined as the sum of shape functions is equal to 1 at any location of your domain. We look at the reproducing conditions, and the idea behind this mathematical notation is basically that if you are adding a function, you should be able to get that function back from the formulation, right? So in this definition, what we say is that indeed you can find coefficients or degrees of freedom that can reproduce a linear behavior in X and in Y. We also define the spaces. We started by the standard finite element space. We look at the DE-FEM space, and this was in a way, let's say, enriched over the linear finite element space. You can think of it as basically adding something that is nonlinear to an enriched space. And then we define the generalized finite element space by first defining the enriched space, right, that contains these enrichment functions and enriched degrees of freedom. And and then by adding the hierarchical space, the enriched space, we're adding that to the standard finite element space, and then we're calling that our GFEM, or generalized finite element method space. Okay, and then we arrive to this equation that is the crux of the course, and is basically what this lecture is going to revolve on. So the idea is to explore different types of enrichment functions depending on the problem that you have at hand. So if you have a fractal mechanics problem, then you will want to choose L alpha J in such a way that it can reproduce a strong discontinuity, right, a jump in the field. Or if you have a problem that is, let's say, composite material with different phases, you want to add a function that really reproduces the jump in the gradient of the field, right, and so on. So let's look at a very simple example to start this second lecture. We're going to look at a very simple example to see how you actually implement GFEM, right? So say you have a bar, just a bar element, very simple, and then we have two nodes, node 1, node 2. So our index set IH, that is going to be equal to the index set as well for the enriched part, is equal to 1, 2. This is our index sets. That means that I'm going to have two enrichment functions. So M alpha is going to be equal to 2. Yeah. And of course alpha belongs to that index set of enriched nodes. So I'm basically having one element, two nodes, and what I want is to enrich both nodes, right? So each node with two enrichments. Okay, so if we write our approximation, what we get is Ux is going to be equal to the sum alpha in the index set 1, 2. Remember that U hat is a notation that we chose to represent the standard degrees of freedom. The same thing here. and then my j is going to go from 1 to 2 because m alpha is equal to 2, and we have our other notation for the enriched degrees of freedom using a tilde. Okay, so that's it. This is our generalized finite element approximation. We just rewrote that complex expression that we saw before for a simple element in 1D, right? Where the standard nodes are just numbered 1 and 2, and then we are basically using two enrichment functions. Yeah. So if we expand this, let's try to write this in matrix form, right? Let's expand this. You can say, well, if you just take into account first all the left part also, so everything that deals with the first shake function, you have the partition of unity shake function. That is basically going to be this term here, this one. Then you have phi1 L11, which is this term here when alpha is equal to 1 and j is equal to 1, and phi1 L12. So still alpha is equal to 1 and j is equal to 2. I'm just rewriting that expression in matrix form, okay? And then you have phi2, and the same thing happens. You have phi2 L21, phi2 L22. And that is going to be multiplying our degree of freedom vector. And if you look at the first one is my standard FEM degree of freedom that I just called U hat 1. The next two are enriched degrees of freedom, so I call them U tilde 1 1, U tilde 1 2. And then you have this. The next one is a standard FEM degree of freedom, U hat 2, U tilde 2 1, U tilde 2 2 are the other enriched degrees of freedom. This is the way you would write it in matrix form. So you can say, well, how about we call all of these here N, and then all of these we call UE. Suddenly we have a system that we call NUE, which is exactly the same system that we had before for standard FEM, and which is exactly the same system that we had before for PFEM. So in this regard, GFEM is no longer different than what we have seen already in advanced FEM. Yeah, that means that it's just a matter of bookkeeping. If you have enrichment functions that are acting in an element, right? You just find a way to add to your container, to your shake function vector, and to the array that contains the shake function, and to the array that contains the derivatives of those shake functions. You just add those in the back, or you find a consistent way to do the bookkeeping. Then the rest of your implementation remains the same, with some subtleties when we're dealing with discontinuities, but for the most part, for general enrichment functions, it is just a matter of bookkeeping and then obtaining an expanded arrays that take into consideration these enrichment functions. That's all there is to it. Of course, you could argue why you chose that arrangement. We could have chosen a second arrangement, and indeed we could have said, well, how about we write this, and then first we take into account all shake functions first, so we can rewrite this as phi1, phi2, and then phi1 L11, phi2 L21, phi1 L12, Phi2 L22. And if I do that, well, my degrees of freedom are going to shift order. So first I put all the ones that are standard. U hat 1, U hat 2, and then the next follow. So you have U tilde 1 1, U tilde 2 1, U tilde 1 2, U tilde 2 2. And that is another way to write this equation. And in fact, this is the way I decided to implement myself GFEM and the other enriched formulations I've been working on. I find it easier in terms of implementation to just basically use whatever you had from the standard FEM, and if you have your arrays that already contain information about the standard shape functions and the standard shape function derivatives, then I would expand those, right? And that's the way you would implement in a computer. Then we are ready to solve, right? Once we have this bookkeeping in place, besides some subtleties, because let's say the computation of derivatives, now you have to apply chain rule. Other than that, and increasing the number of integration points, everything that you learned before in the advanced finite element class remains the same. Okay? Yeah, questions? Okay, let's move to another example, and then we're going to start by looking at our first enrichment functions. Who can think of very simple enrichment function? What's the simplest enrichment function that you can possibly think of?
Quadratic.
What are those? Polynomials. Those are the simplest enrichment functions you can think of. Can we enrich with polynomials enrichment functions? Yes or no? Yes, we can. We just discussed there's going to be a problem because if we add a linear polynomial, that is going to create some linear dependency because we can already represent linear behavior with the standard partition of unity, right? So we're going to get into this singularity problem that we are going to discuss in a few minutes, but we can enrich with polynomials. In fact, you could get, let's say, the P version of the generalized finite element method, if you will, okay? And those are the first enrichment functions that we're going to look at. So we're going to call these shifted and scaled enrichment functions in what we are going to term the P version of the generalized finite element method. Yeah, so given x, x squared, x cubed, x to the power of p, find a suitable high order polynomial enrichments that can be used with the framework, with GFEM. Okay? So the basis or the set of enrichment functions that we're going to work for this have this form: x minus x alpha divided by h alpha, x minus, well, let's just copy that. Okay, So what you have seen is that if you take, let's say, the value of alpha equals 1, then I'm going to have x minus x1 divided by h1, x minus x1 divided by h1 squared, and so on. And what you see here is that I'm basically creating enrichment functions that are shifted so that the value at the corresponding node is equal to, what is the value at the corresponding node of this function? X minus x1 at location x1 is equal to 0. So you see I'm shifting the polynomial in such a way that at the location of the node is equal to 0. And at the same time I'm dividing by h alpha, and h alpha is actually the size of the cloud, this length. Remember that we're working in 1D. So remember that the cloud is basically the domain associated to that node, right? Or the elements that are connected to that node. So we're basically talking about that length. And we are scaling. Why do you think we're scaling? What are your guesses here? Why are we dividing by h alpha and h alpha to the power of 2 and to the power of 3 and so on?
Yeah, because when you take a point, we have contributions from all the 4 elements, so we divide by h alpha so that we get the average.
No. So we are actually dividing by h alpha because this basis is not very good in terms of condition number. If you remember, we discussed this in advanced FEM, right? We said that if you take x, x squared, x cubed, as you increase the polynomial, right, the polynomial, let's say, interpolation order, all those functions are going to look like more close to one another. And so it's like the higher you go in P, then you are not adding more information. And then we decided to work with what type of polynomials? Legendre polynomials, right? Because those were orthogonal. So in GFEM, this basis is actually scaled so that you have a better condition number in your system. It improves the condition number. Now, of course, the basis has not changed much, so it is not going to be as efficient as working with Legendre polynomials. Yeah. So can we work with Legendre polynomials here? Yes or no?
Yes.
Yes. Yeah, you can work with any function you want. So you can already see that if I work with Legendre polynomials, that is going to be a better basis than this one, right? To enrich my solution. Okay? So making the function equal to 0 at the node is very important. Very, very important. Who can give me a reason why it is important? Let's take a look again at my main equation for this course, this one. So if I look at this enrichment function, and that enrichment function is equal to 0 at the location of the node, that basically means that this term is equal to 0. We get back a standard FEM. Yeah? And this has a very important consequence, because if we get back a standard FEM, we get back all the nice features of standard FEM. And one of the nice features is that we can actually impose Dirichlet boundary conditions in a very straightforward manner. Right? And that is what is happening if we choose this basis. By shifting, I make the enrichment equal to 0 at a location where I need to enforce, let's say, a non-zero Dirichlet boundary condition. Yeah, and I can do so in the same way as I was working in a standard FEM, because the enrichment function at that location is equal to 0. And that is very good. Okay? If the enrichment function is not equal to 0, we can no longer enforce Dirichlet boundary conditions in a strong form, or the way we did it in standard FEM, but we have to use some other approach to enforce boundary conditions. And that is actually a really complex topic that we are not going to try to delve in this course, because there are many ways to do that. You have Lagrangian multipliers, you have the penalty method, you have Nietzsche method, and multiple point constraints. I mean, there are different ways to enforce Dirichlet boundary conditions where when your enrichment functions are non-zero at those locations, right? But for the most part, boundary conditions of Dirichlet boundary conditions need to be enforced in some weak sense. You cannot enforce them strongly. Okay. So what is let's write that down. So the advantages of using this form. Enforcing Dirichlet boundary conditions is straightforward because this is equal to 0 at x alpha, and so we get our standard at that location at that node. We have our standard FEM term only, and then we can basically just impose that prescribed degree of freedom there. Now the disadvantage and we discussed a little bit about this. There is linear dependence. Yeah? If we look back at what we wrote earlier about our reproducing condition, sum x alpha u alpha, this is equal to x. So I just have replaced here, this is basically my standard degree of freedom u alpha. I just replaced by the value of x at the location of the node. That is equal to x, right? And this is coming from the standard FEM component. So let's call that 1. Now, if you take the generalized term, the second term of the approximation, then you have phi alpha, remember? And then I have x, and then I have multiplied by 1. So what I'm doing here is I am choosing this guy here. This is my enriched degree of freedom that I call, remember, tilde. So this is going to be u tilde alpha 1. And this guy here is my enrichment function L, right? So this whole thing here is my generalized enrichment function phi alpha I. Notice that I changed again phi, right? And this is equal to x multiplied by the partition of unity, which by now you know is equal to 1, and this gives me x. So what do we have here? We have that the standard FEM term can reproduce x, and the generalized term or the enriched term can also reproduce x. So you get into this, well, if you take 1 minus 2, that is equal to 0. And it is causing a very big problem. So using a linear enrichment function basically creates this linear dependency that makes your stiffness matrix singular. Yeah? The problem is that The problem is that we are enriching with functions that can be represented already by the finite element partition of unity. Again, our linear partition of unity, we know it can reproduce linear behavior, so enriching with linear enrichment function is not going to help us. Actually, it's going to make this whole thing much more complicated because we now need to solve a singular system. Yeah? And again, can we solve for that? Yes, we can, but we need to do something in particular. So now I'm going to teach you how to solve linear systems that are singular. Tell me.
So this is just applicable in the case of, for example, edge crack, where we have a crack on the boundary. Because otherwise, let's say if we have like a central crack,
yeah,
we don't need any boundary conditions in that element close to that, so we can use something else.
This has nothing to do yet with cracks. Okay,
Yeah,
we're just
thinking about singularities.
Yeah, no.
Jobs, so.
In those cases, if you are using singular enrichments, you are really adding something to your standard finite element basis that was not there before. So you won't have this problem of singularity, right? This problem arises because you're adding something that you already have, right? Think about it in a different way. Say you add, how can I explain it in a different way? Say you have your well, we can extend it to PFEM. If you have your PFEM basis, and then you know that introducing a linear function is going to cause a problem because that can already be reproduced by your nonlinear the entire PFEM formulation, and if you add a quadratic enrichment function, it's also going to give you trouble, right? So as long as you're adding to the formulation something that can already be reproduced, then you get into this issue with linear dependency. And you get into a singular system that you can actually solve for, but you have to do something special to solve that system. And that is what we're going to look at now. Because there was a very simple algorithm proposed by Babuska as well. Babuska has been really the mastermind behind many of the methods that we see today, right? Babuska is really one of the fathers of, I guess, current finite element technology. Okay, so he proposed one very simple approach to solve for this problem. Okay. Well, if you have a singular system, the idea behind what I'm going to explain is basically that you perturb your system so that it is no longer singular, right? If it is no longer singular, you can solve for it, but then the solution is going to be close to the solution of the singular system, but not quite the same. And so there is going to be some residual there, right? Now, if I can work out that residual in a way that I can improve my solution to get a better approximation to the singular system, to the solution of the singular system, right? Then I can get an improved approximation, right? An improved displacement field, and I can continue doing that iteratively until you approach the solution of the singular system with some tolerance. That's basically what it is. It's some sort of iterative refinement of your solution vector, starting from not a singular system, but from a very badly conditioned system. That is basically the idea behind this algorithm. So let's see how we do it. So suppose we have a linear dependent system Ku equals F, Yeah. What we're going to do is we're going to transform that system. And I'm going to basically have K, my U is here, equals to F. And I'm going to use some matrix here. I'm going to call this T. It's a special matrix. These are matrix. T, T minus 1, T. Yeah. This is going to become my new K matrix. You know already T, T minus 1, that is equal to the identity matrix. So the transformation is valid, right? So this whole thing I call U, and this whole thing I call F. So this is my transformation. So I basically take my system and I modify it using this matrix T so that I get an interesting property. And what I want to do, to be able to perturb the system, I want to be able to get something that basically T allows me to get a simple system that I can perturb. So if you define that T matrix, Tij is equal to the Kronecker delta divided by the square root of Kij, that basically means that Kii in your system is equal to Kii divided by the square root of Kii Kii. And this is equal to 1. Yeah, and Kij is equal to Kij divided by the square root of Kii square root of Kij. So what did I do? I just used a matrix in such a way that pre and post multiplying by my original stiffness matrix, I get a new stiffness matrix that has in the diagonal all values equal to 1. That is what it's doing. Of course, you can immediately see that since I am basically dividing it, so this Tij is defined by delta ij divided by the square root of k tilde ij. So then you can already see that the diagonal values that you have on your original stiffness matrix cannot be equal to 0, because then this whole thing breaks down. Yeah? Okay, so once we have that, we can perturb the system. So now that we have a workable system that we can actually modify, we perturb it. And then we obtain a new version of K, that is a perturbed system. So that we get some K, let's call this K epsilon, and is equal to my modified K plus some epsilon parameter that is very small multiplied by the identity matrix. Yeah? Where epsilon is a small scalar usually in the order of, let's say, 10 to the minus 10. Something very small. Very small. So you are still very close to your original system, right? But it's no longer singular. So it's very badly conditioned, but it's not singular. So since it is no longer singular, then we can solve. And as I said, well, we obtain our first solve. We're going to solve Ke or K epsilon u0. U naught is basically our first approximation of the displacement vector. Is equal to f for u0. And we can do this because, again, K epsilon is not singular, but is badly conditioned. But we can still solve for it. Yeah. And then we can compute the first residual. So if we obtain this value of u naught, how can we obtain the residual? What would be the residual? Who has a guess? Let's call that R naught, my first residual. Now, if I look at the residual, right, then I need to look at the original system. Right? So if K u is equal to f and u is the exact solution, right? So then K u minus f is going to be equal to yeah, that is your residual. But if K u minus f and basically u is the exact solution that I'm looking for, Ku minus f should be equal to what?
0.
To 0. And so if Ku minus f is not equal to 0, that is what I call my residual, right? So right now, so far, you see that I have obtained a first approximation to u, right? But there has to be some residual because I am not using the original K matrix, I'm using the perturbed matrix. So how do I compute my residual? Yes, so it's going to be f minus k, but that is my original k, not my perturbed k, u0. That is my residual. Clearly, this is not going to be 0 because we did not use the same stiffness matrix, right? We use a perturbed matrix, but it's going to be very small. So now the whole process starts, you are iterating, and we're following this procedure in such a way that this residual goes to 0. That's all we're doing, okay? So we compute our first error. So if you look at the residual, we say, well, R naught is equal to f minus k u naught, which is equal to k u, which is the exact solution, right? That's my value of the force, minus k u naught, which is equal to k u minus u naught, and this I call my first error, right? This is approximately equal, so my error, let's bring this whole thing down so I have more space. This is approximately equal to k epsilon e naught, because k is approximately equal to k epsilon. Yeah? You guys are following? Are with me? Okay. And now we obtain a new solution vector using that error. Is equal to u0 plus epsilon, so plus e naught, and we can actually get e naught because we can solve for that, right? We can solve for that because here I'm saying, well, I have R naught, and I have said right now in this equation that R naught is approximately equal to k epsilon E naught. So I can solve for E naught by just inverting the system again. Yeah, and I have now what would be the first value of the error. Keep in mind that so far I am I am basically inverting my matrix only once. So I do the LU factorization only once in K epsilon, and we're basically reusing that information as we move along. So the complexity of the algorithm doesn't grow very much. We will talk about that in a minute. But once we have, so let's basically write that explicitly. We can basically solve for E naught, which is the first error, which is approximately equal to K epsilon minus 1 R naught. So once we have that, we update our solution vector to U1. And that is our improved guess of U. Yeah, and then we continue this process. We get our new value of the residual. We obtain the new value of the error. We update the displacement until basically that residual goes to 0. And that is the iterative procedure that we follow to solve for a singular system. So let's make one more step. So after this we get R1. So this is basically the same thing as we wrote before, is F minus K into U1, not U0 anymore, and this is equal to KU, which is the exact value that we're looking for, minus KU1, which is equal to KU minus U1. This we define to be E1, so it's the second error, and then we solve for E1 because we said that this is approximately equal to K epsilon inverse R1. And once we have that, then we update our solution and then we call our new solution U2 is equal to U1 plus E1. Yeah, and so on. And we do this until, well, until some norm falls within tolerance, right? And what we do is we compute a norm that looks like this: EI transpose K EI and we normalize that until this whole coefficient or ratio follows within tolerance. Yeah. So again, it seems complex, but it is actually quite straightforward. Let's go through it again. The idea here is that we start with our original system, and because that K is singular, we cannot solve for it. And so what we do is we transform the system with this T matrix that is defined in such a way that the transformed system has all ones in the diagonal. Yeah. If they have all ones in the diagonal, well, I can perturb the system by just multiplying epsilon with the identity matrix. So you see that all the elements in the diagonal are no longer going to be equal to 1, but 1.00000001, depending on that epsilon parameter that you use. So now the system is perturbed, no longer singular, but is badly scaled. And then we follow this iterative procedure, where the first thing we do is, well, we solve for our first guess U0, right? We compute what would be the residual for that U0, because since we didn't use the original K, this computation F minus K U0 is not going to be 0. It's going to have some finite value, but it's going to be very small because the two systems are very close to one another. Okay, and then we compute the error. With the error, we can update our solution and we continue doing this iteratively until some norm of the error falls within tolerance, and we can exit the whole iterative procedure. And then we have found one set of values. Now let me ask you something. This is something that you all guys should know about. But when you have a singular system, how many solutions you have?
Infinite.
You have an infinite number of solutions. So we have found in this way one of those possible solutions. Okay? And it is enough to really be able to write down the whole approximation and to basically see how the displacement using this generalized finite element method works. One important remark in terms of complexity here is that you see that what are the types of operations that are involved. You see that basically what we need to do is to invert this system, right? So we solve for u naught, so we have to invert k epsilon. As you know, we never really invert a system. We do LU decomposition, so we decompose that matrix into LU factors, lower and upper triangular matrices that we can then use by using forward and backward substitution to solve for the problem, right? So that is one of the operations, and then the rest is basically just multiplication of matrices with vectors, right? So the complexity of the algorithm is just basically to solve that, to do the LU factorization of that k, which is the same as the original standard finite element problem. Yeah, you just have that factorization and then you start this loop, but this loop only consists of matrix vector multiplications, and that's it. So the complexity doesn't go very high. So let me finish now by saying here the total complexity. And with this I'm finishing, okay? I think we went over, but okay. Any questions up to this point?
Yeah, perhaps you can, you have already mentioned it, but if so, you can repeat.
Yeah.
What is the motivation of adding or implementing an enrichment that leads to a singular k?
What is the motivation? You really don't have a strong motivation there. So if you can bypass the enrichment functions that are not going to lead to anything useful, that is the way you would actually do it. So if you want to use this set of polynomial enrichment functions, all of this lecture is basically telling you how you can do it if you decide to include the linear polynomials. But you could also bypass the linear polynomial altogether and then just go straight to quadratic. That is also a possibility. Both work. Actually, the second one is simpler.
So
Yeah.
So why do this?
Why?
So why you would implement the first
I guess I'm telling you all of this because initially when people started to investigate the method, they got into this problem. So I'm saying you this because you may think, well, what is the simplest polynomial that I can ever encounter? And then you say, well, I'm going to try the method with linear polynomials, right? That's the simplest enrichment that you would possibly add. And then you basically hit a wall, and then you say, well, this method is really not useful because it gives me a singular system. So, but it's just with this case, right? But now you know about this, then of course the idea is not to get into that trap. But in the project, I'm asking you to do this.
Okay.
Okay, so talking about the project, I will post the project next week already, so that you already see what we're going to be dealing in the course, but it's going to follow a similar idea than what we did in Advanced FEM. So it's going to have one simple 1D problem, and it already contains a lot of what you guys know, convergence rates and so on. And it's going to have a nice 2D problem, so that you can really see the working of this methodology in a more like a real setting, which is what we do actually in our research group. We are dealing with this type of more complex problems, but you're going to have a very simple problem. So it's basically a domain with a circular interface that you have to solve mesh independently. Okay. All right. We see each other next class.